Hello and welcome to the Stardog Academy training on high availability. This is Joseph Hayes, one of the senior software engineers at Stardog. To let you know a little bit more about me, I love helping customers maximize the value they can get from their data by implementing innovative solutions to complex data problems. Today, I'm going to walk through Stardog clustering for high availability. In this training session, you will learn how to become familiar with Stardog cluster usage, understand different node purposes, build a cluster with Zookeeper and load balancer nodes, and set up a cache node to cache a virtual graph. Let's get started. This begins the section on Stardog Cluster. Now, why would you want a cluster? For one big reason, it provides high availability. Because data is replicated across all the nodes in the cluster, if any node goes down, the others can pick up the slack and make sure there's no disruption of service to the clients. In fact, a cluster, no matter how many nodes it has, will look like a single Stardog instance to clients. That ends the section on Stardog Cluster. This begins the section on architecture. A Stardog cluster is made up of several types of components. Let's talk about them. First, we have Zookeeper nodes. There will be at least 3 Zookeeper nodes within a Stardog cluster, and they act together as an ensemble to provide centralized configuration information and distribute synchronized data updates throughout the cluster. They also manage our cluster locks and keep track of transaction IDs and node participation in the cluster. There can be several types of Stardog nodes. There are standard nodes, which means a Stardog node will either be a coordinator or a participant. We're going to be talking more about coordinator nodes as we continue. There can also be cache nodes. Cache nodes are used to scale out and reduce the load on upstream data servers. When a cluster receives a user request, it'll first check if it has the answer cached before returning results. There can be standby nodes. Standby nodes are closely synced to the cluster. This allows administrators to safely run database and server backups without taking CPU cycles from servicing user requests. In addition, a standby node can upgrade to a full node in the event that some cluster node fails, or if the cluster simply needs to be expanded. We can also have a load balancer. Any load balancer can be used. They provide liveness checks that a load is working. They provide health checks. Is it a full participating member of the cluster and ready for traffic? They can also be configured to provide direct access to the coordinator node. This will be appropriate if we want to have a route directly to the coordinator for administrative tasks. So a cluster guarantees that all the nodes are consistent. Those nodes that fail operations are expelled from the cluster, and they must resynchronize before they can rejoin the cluster. That coordinator, the coordinator node, ensures and maintains consistency across the cluster. At the same time, any node can handle a client request, but we can always send it directly to the coordinator node if we need to. Let's dive in a little deeper. So again, one node serves as the coordinator. It's going to orchestrate the transactions. It's going to maintain consistency. If it fails, a new coordinator will be elected from the other Stardog nodes within the cluster. Those other nodes otherwise serve as participants. There are several types of locks that can be used within a Stardog cluster. There can be an admin lock, which gets acquired before any administrative operation. There can be a read lock, which gets acquired before any transaction. And then finally, there's a cluster join lock. Now, just some notes about the cluster join. Transactions are held in a queue and processed in a queue. So whenever you ask or request a cluster lock, all the transactions that are in the queue ahead of it must complete before the cluster join lock can be granted. Now, once a cluster join lock is enabled, this will block all the writes, and it'll also block any other transactions. And the cluster join lock must be released before those other transactions can be processed. So remember that a cluster join lock can be very disruptive to the cluster as a whole. When a node wants to join a cluster, we need to determine, do we need to lock the cluster? And does the node need to sync its data? We're going to try very hard to not lock the cluster. By default, we configure it so a node will attempt 3 times to synchronize its data before we attempt to get a cluster lock, so we can lock the cluster and force the node to join. Now remember that those transactions and these locks are in a queue. So if there are a lot of transaction writes, that joining node has to wait till those writes are processed. And even when it attempts to obtain a lock, it has to wait till the writes that are ahead of the lock are processed. And nodes attempting to join the cluster will attempt to sync before they go to the step of obtaining a lock. Now, when we're synchronizing across our nodes, there are several actions that can be triggered. This is not a comprehensive list of the actions you may see, all right? But they just give you a flavor and the what could possibly trigger them. Here are some additional actions that you can see that it may occur on a given node. That ends the section on architecture. This begins the section on implementation. Here is some sizing, performance, and best practices you can use when implementing a Stardog cluster within your environment. Remember that Zookeeper fault tolerance works best with an odd number ensemble of nodes. So at least 3, but any odd number will be works best. Larger Stardog clusters tend to be more performant with reads and less performant with writes. You can see our blog post, Tuning Cluster for the Cloud, on the Stardog blog for additional tuning advice. Let's talk about some specific deployment examples. We can have a load once, read many type scenario. This is where a Stardog node in the cluster will mount a volume created from a snapshot, bulk load all the data at startup, and once it joins, it can automatically start responding to read requests. And the load balancer can send requests to it in a round-robin fashion. There's no blocking here because everybody's joining fully synced. Now, we may also have a situation where throughout the business day, data is constantly being written to Stardog. But then after the business hours, there's not much activity at all. So in this use case, we want to make sure that we don't have our joining nodes blocking any writes. So we can actually configure Stardog to never forcibly obtain a join lock. And if you need to, it may make sense in this case to deploy a larger cluster so you can afford to lose more nodes so you can keep up the level of service for the clients. You may have a scenario where you have continuous small writes all the time. There's rarely any quiet time in the cluster with respect to writes, but you do want your nodes to join as quickly as possible. You can actually configure it to obtain a lock on the second attempt. It will block the writes, but since the node will sync without the lock on the first attempt, it should be able to mostly catch up with the other nodes on the cluster. On the second attempt, it will get the lock, but we're now talking syncing just a very small window of data. So the amount of time that writes are blocked will be very, very small. This ends the section on implementation. This begins the section on the demo. For our demo, we're going to use Docker to run a Stardog cluster. Within our cluster will be 3 Zookeeper containers. Here is an example of the Docker Compose file or section of the Docker Compose file we will use that defines one of the 3 Zookeeper nodes. There will be 3 Stardog containers. Please note that you will need a license and properties file, which will be passed in when we build the various images. Here is a snippet of a Docker Compose file that defines one of the Stardog nodes. Here is the Docker file example. Please note that we are copying our license file, our properties file, a log configuration file, and a database driver in to our image. As well as if we had any additional extensions, we could copy those in as well. Here is the example of the Stardog properties file we will use. Finally, we're also going to have a load balancer. We're going to use HA proxy for our example. Here is a snippet of a Docker Compose file that defines the load balancer. And here is the example of the HA proxy Docker file we are going to be using. Basically, we're going to be using the standard image coming off of Docker Hub. We're just going to copy in a specific configuration file. You can get some more information from our doc site about how to set up HA proxy for working with Stardog. We're also going to create a virtual graph for our database. You can see our tutorial section on using virtual graphs for more information. Finally, we're going to have one Stardog container that's going to cache the data in our virtual graph. Now, this can pretty much be the same as the Stardog setup, but just know that you can pass in a blank properties file. Most of this will be configured from the command line when we actually create the cache. Here is the Docker Compose snippet for the cache node. And these are the commands we're going to use to actually create the cache. So just to run through, this is the actual Docker Compose file I'm going to use, where I'm defining out my Zookeeper nodes, my Stardog nodes, and my cache. And in addition, just so I have somewhere to put my virtual graph, I'm going to start up MySQL as well. All right. Okay. So let's go to our terminal, and we're going to run the Docker Compose file this way. Okay. Normally I would run this as in daemon mode, but I just want you to be able to see the various log messages from everything starting up. Okay, I'm just going to give a minute just so Stardog itself ends up running. So what I can do is, once everything starts up, I'm going to have, and I'll be able to see this using Docker Compose process PS, or I can use Docker PS, right, to see the various nodes I have running. So we have MySQL database, we have a Stardog cache node, a Stardog load balancer, 3 Stardog nodes, and 3 Zookeeper nodes. Okay? All right, so next I'm going to create a virtual graph on my Stardog cluster, and I'm also going to create one on my cache node, because of course we want to cache that virtual graph. So the command looks pretty much the same, it's just where are you sending it, okay? So first one, I'm going to do virtual, sorry, command history isn't working. Okay. So the command to create a virtual graph is virtual add, and then we're going to pass it a properties file. Oh, sorry, got my path wrong. All properties and share sample SMS. Okay, so I'm passing in a properties file and I'm passing in a mapping file. Let's take a look at these quickly before we run the command. My properties file simply defines how am I connecting, how will Stardog connect to MySQL. So this is basically, pretty standard JDBC, arguments that we're sending in, the URL, username, password, and what driver do we use. The mapping file is where do we want to get the data from? Notice the from SQL section here, right? So we're doing a select star against sample.sample. And then we are going to define what we want to do with the data. So these are the various items that come back. And then we simply can create triples that we're going to insert into Stardog. All right. So let's now run our command. All right. Okay, so we added the graph. And the way we can check this is simply by running virtual list against our server. Now, we don't want to just create the virtual graph on the cluster. We also need to create it on the cache node. And this is because the cache node will need to pull the data from the virtual graph when it refreshes itself. So we're going to repeat the command, but instead of sending it to the cluster like we did the first time, I'm going to add in the server argument, and I'm going to pass in the address of my cache node. So it's 5825. So how do I know that? Because when I ran docker compose ps, I see the name SDCA, and I see the ports defined. My local port 5825 is pointing to the 5820 port on the cache node. All right. So again, I'm going to repeat this command against the cache node. Okay, good. So I now have that. And again, just to check it, I can run virtual list. Okay, good. So now I have a virtual graph on both my cache node and also on my cluster. All right, so excuse me, I have a virtual graph on my cache node and on my cluster. Yes. Okay. So now what I'm going to do is I am going to create the actual cache, right? So first I'm going to tell the cluster what my cache target is, all right? Meaning what node am I going to be looking at here? Okay, so the command is stardog admin cache target, right? Add, I give the cache name, so we'll call this cache 1, right? And we're going to say it's at SDCA, that's my host name for this, 5820, right? 20. And we're going to say that you need the credentials admin. Okay, so the target was added, all right? So, and we see that there was some log messages sent to us from Stardog Node 1 that we successfully created Stardog cache. Now we can check this again by running the command cache target list. Okay, so there we go. Our cache target is now registered and we can now use it. So now let's create our actual cache. So we're going to say create, cache create, and we're going to call it cache sample, right? And it's caching graph virtual sample. And the target will be cache 1. All right, so this is telling the cluster to create a cache for the virtual sample VG and to put it on cache 1. Now, remember that if I'm going to cache a virtual graph, that virtual graph needs to exist on the cache node and in the cluster. Okay, so we cached the graph. As we can see, it's not very big, but we have cached it successfully. So let's take a look at this. Again, let's check our work, right? So I can do that using the cache status command, and if I run it with all. Okay, so this is telling me that I have a cache called cache sample. It's of type graph. It's on cache 1. The size is 12 triples, and it gives the date and time of when it was last refreshed. All right? So that's how we can, create a virtual graph on both a cache node and on a cluster, and how we can create a cache for that virtual graph on our cluster. All right? So now let's talk about, going back to our slides, monitoring. So I have 3 commands available to me for monitoring. I can use cluster info, I can use cluster status, and I can use cluster metrics. So let's see what kind of information each of these gives me. I'm going to go back to my terminal here, and I'm going to run the first one, which is cluster info. So cluster info is going to give me information about the nodes within the cluster. So I see I have 3 nodes in my cluster. It tells me where I can find my coordinator and which 2 nodes are merely participants. All right, so that's cluster info. The second command is cluster status. I'm going to run it through a pager just because of the amount of output it gives out. All right. And cluster status is the equivalent of going and actually running Stardog admin server status on each of my nodes. Okay, so there we are for the coordinator node, right? I get the basically I find out what version of Stardog it's running, what its heap memory is, some basic information about the node. All right? And I get this for each of the nodes within my cluster. Okay? My final command, my final monitoring command is metrics. Again, I'm going to run this through a pager just so we get a sense of what kind of information is returned. And you see that for each of the nodes, I get, a number of metrics returned to me. Notice these are set up metric name, colon, and the value. And this is so you can easily parse it in your, log analysis software, such as Splunk or Datadog. All right? And I will get back these metrics for each of my nodes. And I can, like I said, I can use my, parsing software to kind of pick and choose which ones I really want to watch. Right? Okay, so that's our monitoring commands for the cluster. Now, when I'm backup and restoring for the cluster, all right? So here we have steps on how to do it, all right, at a high level. Now, when we do this, please follow each step, right? And because this will minimize the downtime and also minimize the chance of any data loss, right? And when you restart the cluster, because basically what we're going to be doing is shutting down all the nodes, performing the backup, and then bringing the nodes back up, right? And when we restart them, make sure that we start them one at a time. Always start with the coordinator and make sure that each node has successfully rejoined the cluster before you continue on. We're going to follow something similar when we actually upgrade our cluster. We're going to shut down the cluster, and then we're going to perform the upgrade, and then we're going to bring our cluster back up node by node. And remember that we want to start each node, starting again with the coordinator. We want to make sure it has successfully rejoined the cluster before we start the next node. This ends the section on demo for Stardog High Availability Training. That concludes the Stardog Academy training on Stardog clustering for high availability, where we reviewed how to become familiar with Stardog cluster usage, understand node purposes, build a cluster with Zookeeper and a load balancer, set up a cache node to cache a virtual graph. Thanks for following along. If you have any questions, please review our frequently asked questions page or head to docs.stardog.com for additional information.